Hello, my name is Shuhao Zhang. I'm currently assistant professor at Singapore University of Technology and Design. The paper I'm going to present is regarding experimental study of parallelizing intravenous join and multicore processors. Intravenous join is a special type of stream join operation that joins two input streams over a single window. It receives little attention in the big data area, despite that it is very important and practically used for operation. I will first describe a use case of stream join, in particular the intravenous join, and highlight why we need to pay attention to it. Then I will discuss our experimental methodology, some evaluation results, followed by the conclusion. This figure illustrates how Uber detects car accident, presented in Flink Forward 2019. There are several features that strongly correlated to car accident, including both the GPS location information and accelerometer sensors. From the GPS location, we can extract information where the car stops. But the car stop may be because of the red-green light or simply a drop-off. So it does not directly imply a car accident. The accelerometer sensors at the same time can detect if there's a sudden shake on the user's phone. Combining both signals could infer a potential car accident. Subsequently, the combining of these two input streams has to be done in real time so that Uber can quickly respond accordingly, and that relies on fast stream join operation. By definition, joining data streams perform over infinite input tuples and hence never ends. In practice, users typically formulate queries that compute joins over a bounded subset of streams called windows. Inter-window join joins of two input streams over a series of windows. Most existing studies focus on inter-window join operation and especially pay attention to the case where there are windows overlap, or called sliding windows, as illustrated in the figure. In contrast, the intra-window join joins over one window of data streams, and it concerns the case where the users are only interested in one particular subset of streams. That is one window. One example is the Uber's detection of car accident. At each time, the focus is to join two input streams over the duration of the same trip. That is one window. Another example is at the Pinterest, where the developers use Flink to join the activation record per user for a single time window of 3 days. Early work of intra-window join historically focused on single-threaded execution efficiency and is no longer suitable on modern multicore architectures. Recent works on parallelizing stream join processing are geared towards inter-window join. Only two works concerns parallelizing intra-window join operation. We observe that there are actually many alternative ways to implement parallel intra-window join, and it remains unclear which way is the most efficient approach. There are particularly three main challenges in resolving the aforementioned literature gaps. First, a significant number of join algorithms have been proposed. As a result, there are many design options available, such as lazy or eager, sorting or hashing, and so on. Second, there are multiple common performance metrics for stream processing, including throughput, latency, and progressiveness. Those metrics meet different application demands and can sometimes conflict with each other. And third, modern hardware features such as SIMD, multicore parallelism, and NUMA are bringing further questions in the completion of different algorithms. Pirate studies are usually biased towards a subset of algorithms and performance metrics. Furthermore, some are not being evaluated on modern multicore processors. In this work, we propose the first comprehensive benchmark suite, including 8 different algorithms, 4 real-world datasets, and 1 carefully designed synthetic dataset. We then evaluate the benchmark on a recent multicore server with different hardware settings. It is difficult and unnecessary to implement and evaluate all join algorithms in our benchmark suite. Instead, we propose to select a representative subset of join algorithms so that they can well cover the key algorithm design aspects of intra-window join. That is the execution approach, join methods, partition schemes. Let's now discuss the design aspects one by one. The first design aspect is the execution approach to handle data streams, namely lazy or eager. The lazy approach first waits for all input tuples of the constraint window from both input streams to arrive, and then joins a complete set of tuples. In contrast, the eager approach aggressively joins upon the arrival of only a subset of input tuples. The second design aspect is join method, namely hash or sort. A hash-based algorithm always follows the principle of build and perp, where build is to construct the hash table and perp is to generate matches by querying the hash table. A sort-based algorithms always follow the principle of sort and merge, where the sort is to sort both the input relations, and the merge is to merge the sorted relations while generating matches. The last design aspect is the partition schemes, with or without physical partitioning, stands for whether the algorithm replicates input relations among threads before execution. Content-sensitive or insensitive distribution stands for whether the algorithm shuffle or key-based partitioning input relations among threads. We studied 8 algorithms for parallelizing intra-window join, including non-partition join, radix partition join, multi-way multipass, symmetric hash join, and progressive merge join with join by tricks and join by click-queue partition schemes. They cover both lazy and eager approach, as summarized in the table. Typically, the 4 relational join algorithms are used to implement the lazy approach, while the specifically designed stream join algorithms are used to implement the eager approach. They also will cover both hash and sort join methods, the non-partition join, radix partition join, and symmetric hash join. They belong to the hash join methods, while multi-way, multipass, and progressive merge join, they belong to the sort join methods. Finally, they cover different partition schemes. Take note that for the eager join algorithms, their partition schemes are based on either the join matrix or join by click-queue partition schemes, where the join matrix, short-term as JM, is content insensitive stream distribution scheme, while the join by click-queue scheme, short-term as JB, is content sensitive. We designed a benchmark consisting of 4 real-world data sets, including the store, Carol, YSB, and DBS. They cover a wide range of workload features, including the arrival rates, which stands for the number of tuples arrived per milliseconds. Key duplications refers to a number of duplicates per key. Key skewness refers to the key distribution in the stream, and total number of tuples to join, which can be computed as average arrival rates times the window length. They also cover different arrival distribution as shown in this figure. Particularly, the Stork dataset has a non-uniform arrival distribution, where input arrival rates change rapidly at different timestamps. In contrast, RO has a more uniform arrival distribution. Other 2 datasets arrive uniformly, and their distribution are hence not shown here. To eliminate the impact of different programming languages and compilers, we re-implement 8 algorithms according to their original papers in the same code base. We assume a narrowed tuple configuration with 64-bit length per tuple. This allows us to pay more attention to the join processing efficiency. We use read timestamp counter to measure program process with minor overhead, and use Intel PCM and perf tools to gather architectural statistics of all algorithms. All of our experiments were carried out on a recent multi-core servers containing 2 sockets. To exclude the impact of NUMA, we use only one CPU socket in our experiments. We leave the evaluation of NUMA in future work. This figure illustrates the overall comparison on throughput and latency among all algorithms. We can see that the lazy approach brings higher or at least the same throughput for all 4 workloads, which indicates the higher execution efficiency. While the eager approach shows lower latency in some workloads, in particular the Stork and YSB. This figure shows the comparison of progressiveness of different algorithms. The eager approach, which is implemented based on the specifically designed stream join algorithms, is able to generate matches without waiting for all input tuples to arrive. As shown in this figure, in the Stork, the SHJ-JM algorithm is able to generate matches progressively along the way. Hence, the common belief is that they are able to achieve faster progress. But when lazy approach can quickly finish the overall process, for example, in RO, it can surpass the eager ones early. As a result, eager approach does not always imply faster progress, as our experimental results confirm. We now ask the question, where does time go? We break down the execution of all algorithms into 6 components. Wait is the time spent in waiting for input tuples to arrive. Partition is the time for building the hash table. Is to partition input relations. Build or sort is the time to build a hash table or sort input relation. Merge is the time for merging sorted relations. Probe is the time for probing and the hash table or merge during merges. Other stands for all other overheads such as context switching. Only highlight one key observation here, which is that the lazy approach does spend more cycles in waiting for tuples to arrive in some workloads, for example, Stork and YSB. But if we exclude impact of waiting time, we will see that eager approach actually spends much more cycles in handling each tuple. And in particularly, more cycles are spending in partition and probe phases. We observe that the inefficiency of the eager approach is caused by significant cache misses. There are different cache behavior during the partition and probe phases. During the partition phase, the uncontrolled random data access of content-sensitive partition scheme results in high cache misses in both L1 and L2 cache. While during the probe phase, frequent interleave access to 2 input streams of all eager algorithms results in poor cache reuse pattern. And this especially stresses the L1 cache. We have further discussed the impact of the workload features, different algorithm configurations, and the impact of multi-core and the use of SIMD instructions. Please refer more details of all those experimental results in our paper. All source code and data of our benchmark suite, as well as guidelines on how to reproduce the results, are all available at the GitHub repo. We summarize the main findings of all our analyses in a decision tree. It can guide users to select appropriate algorithms. In a nutshell, no one size fits all. First, we recommend lazy algorithms when arrival rates are high. When key duplication is also high, sorting-based lazy algorithms are better options. And multi-pass scales even better with the number of cores. When key duplication is low, non-partition join and parallel radix join are more effective, and parallel radix join performs better when key duplication is low and the number of tuples to join is large. Second, when arrival rates are medium, progressive merge join with join by clique partition scheme performs the best in terms of all three performance metrics for handling high key duplication workload. While symmetric hash join with join matrix partition scheme achieves much lower latency and better progressiveness for handling low key duplication workloads. However, if throughput is still the key concern, we still recommend lazy algorithms when arrival rates are medium and key duplication is low. Finally, we recommend symmetric hash join with join matrix partition scheme whenever one input stream has low arrival rates, as it is able to eagerly utilize hardware resources. In conclusion, we find that none of the existing approaches perform uniformly the best in all cases. Workload features, performance matrices, and hardware architectures are all need to be considered when applying the right implementation of intra-window join operation. This will naturally lead us to a potential future work. There's a need to developing a adaptive intra-window join algorithm that considers all the factors: workload, metrics, and hardware architectures. Another direction to consider is to further extend this study to include more hardware architectures, such as the NUMA architecture, high bandwidth memory, GPUs, FPGA, and so on and so forth. Finally, our success attempt in bringing the relational join algorithms to joining over data streams indicate the great potential of joint effort from different communities to better support data-intensive stream applications. This is a very general problem with lots of potential. With that, I would like to say thank you, and that's all for my presentation. I would like to take your questions.